how does this all connect to the shapes? Right? Well, if we think about it, let's just get to the more complex version, which is the area between two curves. If there's only one curve, then our rectangle, our base, if you that we're interested in, is going to be the distance between the function and the x-axis or the y-axis, which is basically just means that we're doing f of x or something f of y, if you will. If we're interested in the region between two curves, like this picture right here, what I've just quickly done is I've got f of x and g of x. G of x is my smaller of the two functions over the region. And the first time that they intersect is a, and the second time that they intersect is b. Right? So h is my sample rectangle, if you will. It's the sample base of our geometric shape. Right? So what exactly is h equal to? Well, we can see from the picture that to get the distance of h, we just take the upper function f and we subtract the lower function g, and we get that. So h of x is our f of x minus g of x, and it doesn't matter if it's right here or somewhere to the left or to the right. All right. So this f of x minus g of x, that's going to be a part of all of our integrands. All right. The question now remains, what do we do with this? Because we want the area of a particular geometric shape. Right? So let's look at them one at a time. The first one would be a square. Okay? So what we're looking at is a whole bunch of squares coming off the board towards the screen. All right. Now, if we think about a square, all right, the area of a square is rather simple. All right, it's just side squared. Well, what's one of the sides of our squares? It's h. We have a whole bunch of squares coming off, and h is one of the sides. All right, h is f minus g, so our area would be f minus g times f minus g, or f minus g squared. Now, just be careful here. All right, it's f of x minus g of x, and the whole difference is squared, all right, with the dx afterwards. All right, so this is actually the square of the difference, and if you remember from our revolutions, we actually had each of these individually squared. It was the difference of the squares. All right, so just be careful here. This is actually the square of the difference of the two, and that gives us our area if we're just dealing with squares coming off. Right? What if it was rectangles? Well, if it was a rectangle, and again, we need to qualify it that the height is a certain, the base to height ratio happens to be there. All right, so the k times whatever the base happens to be is our height. Right? It's the same idea. We've got shapes coming off of that zone right there. Okay, but instead of the area being side squared, the area is base times height. Right? Well, the base is our f of x minus g of x. Okay, the height is k times the base. All right, so if the base is f minus g, I'm just going to write this in shorthand real quick. That's the base. All right, and then the height is k times the base. All right, can you see how we have k times the quantity f minus g squared? All right, so let me get my eraser for a second here. So what we're actually going to have here is we're still going to have the f of x minus g of x squared. All right, so let's get that in for our rectangle. All right, it's going to be wrapped and squared. All right, but there's that coefficient k, and it can go either on the inside or quite often it's placed on the outside. That's our formula if we're talking about rectangles being the cross section.